what you do is you use Excel or any kind of program. Okay, so let's have a look at these models. Any questions about this? So this kind of model is called the generalized Beaverton-Holt model. Beaverton-Holt were the first to use the blue model over here applied to fish populations. But then people found that populations didn't seem to have just an asymptotic carrying capacity, but actually as they got to higher and higher levels, they would degrade their environment for that period of time, so that in fact you'd get this overcompensation, and things would be quite bad at very high population densities. So here's some data from a study by a professor at, I think he was down at Riverside, an entomologist. And he looked at populations, the relationship between the survivors and the initial egg density for 4 species of stored product beetles. So how many of you opened a bag of flour and seen worms in there, or seen insects in there? Okay, they're flour beetles, and they're very good. Good source of protein. They're much better than you are at turning flour into protein. We basically need the protein, so you should just don't bother with the flour, just eat the insects. I guess the time's going to have to come when we're going to have to eat insects. Pretty inefficient to eat cows, very bad for the environment, a lot of methane. We're not making enough use of insects, certainly in North America and in Europe. And I think in Asia, people eat more insects. Has anybody eaten water beetles in Vietnam or places like that? You can go in the street markets and eat them. Anybody eat? I've eaten mapani worms in Africa. So you grill them. They're pretty good. Actually, they're not so good. They're pretty lousy, but sort of that one-time thing. You have to say I ate one. Anybody here eat an insect? Yeah, what did you eat? Oh, you ate where? In Southern Africa? In Namibia, okay. The ones I had were rather dark and like, I don't know if they just burnt them. Yeah, no, they weren't great. But anyway, in experiments where Tom Bellows would start out and he would put, he would have a container of flour, and he had 4 different species of these flour beetles, and he stocked them at different densities, and then he had a look at the number of larvae that survived and emerged as adults. And so he was looking at the number in the previous generation. So, for example, he would start with 120 individuals, and he would get 20 out. He would start with, I guess there might be something like 132, and he would get 18 out. He would start with 80, and he would get 29 out, and so on. And he did this for 4 different species, and what he showed is that it depends on the species. So different species have different strategies for avoiding this kind of competition. So some species may be flexible plastic, and if there's less food, they'll still go through the development stage, and they'll make smaller adults. Do humans do that? Sure we do. So if you go back generations, if you go back to Roman times, everybody was a lot shorter there. If you brought up on kind of bread and water and occasionally other stuff, you're not going to grow as big. So there's this phenomena where over the last 3 or 4 generations, each generation is bigger than, on average, than their parents. So if you come stand next to me and you're taller than me, it's not because you're genetically superior, it's only because you had better nutrition as a kid. Okay, well, that's not quite true. So there's genetic variation and there are environmental effects. But to humans, it's quite limited. But with some invertebrates, it can be quite extreme. And fish, for example, keep growing as long as they feed well, and they get bigger and bigger. And the number of eggs they produce, a female produces, is proportional to her weight. So it's better to be a smaller fish and produce some eggs if you can't grow to full size, and then you mature earlier and you have fewer eggs, than to die trying to reach a bigger size. So these are different strategies that one can take. Okay, so you can read about this model, but what we're going to do is we're going to play around with this model. So I have a copy of this model here. And so how many of you want me to build this model now? Okay. So again, I'll do it today, but you're going to start building these models for yourself. But what I'm going to do is I'm going to run it first, just to motivate the fact that it's a neat model, and it's good to build it. Okay, so here's our value of g, and I'm going to make the value of g round about 1. Can everybody see that? And I'm going to make r, if I make r equal to 1, then nothing's going to happen. So let's see that. In fact, it's going to decrease in size because there's some density dependence. So capture, load, exec. And you see that if I make r equal to 1, it's going to go down in size because there's this environmental carrying capacity effect that makes the effective r at a density of x greater than 0, something less than 1. So I'm going to start increasing r, and I'm going to put it in auto mode so that you'll see. Okay, so changing the value of r. Oh, there you see it jumped. So it went from, whoa. So there we see we have at r equal to 1.5, nothing happens. It's at what we call an equilibrium. At r equal to 1.49, it declines, and at r equal to 1.51, it grows. And it keeps growing. And as I make r bigger and bigger, it just grows faster and faster. But eventually it's controlled by this environmental carrying capacity k. So the environment can only produce a finite number, and at some point, depending on the value of r, so as you see, as r increases, the point that it goes to, which, as I said, is equal to r over 1 over k. So as I change the value of r, this gets bigger and bigger. Okay. Yeah. This x, or what? So g, this parameter g is this thing gamma. Okay, so it doesn't have a gamma, I just put a g. Same thing. Okay, that's the parameter gamma. What else did you want to know? Yeah, except that here we're plotting time now, and here we're plotting the value x over time. And it's really a set of points, but what NOVA does is you won't actually see the points that easily, it just connects them with lines. But the fact that it's a continuous line shouldn't fool you, because it's really, I'm calculating it at time 1, 2, 3, 4, 5, so I should just get a series of dots, but NOVA connects them as a line. I think it's possible that I can actually go in here, and somewhere there's a preference, and I can change that, but I'm not going to do it. Let's see, NOVA preferences. No, that's not it. Okay. So there's some preferences in different places that help you reset things. You can change the color background and so on. But we don't need to worry about that. Okay, so here for different values of R, so now I'm going to set R back to 1 and close to 1, yeah. And I'm going to, let's say I'm going to up G. I'm going to make G equal to the value 3. So what I said is that as I increase the value of G, I get more and more of a hump shape. And now I'm going to start increasing R. And to make it easier, I'm going to set this so that instead of going to 2 decimal places, I go to 1 decimal place. So every, let's see, okay, there's R equal to 1.5, 1.6, 1.7, 1.8. So what are you noticing is happening now? What's happening? Let me go back. Okay? So now it's a smooth curve to the top. And now there it starts, little overshoot. So what's happening, I'm getting this effect where, I'm a little too high, and then in the next, I actually come down. So I don't actually grow, I decline. So I keep growing, and I get too big, and this turnover effect now sends me back down to a smaller value. And I approach a carrying capacity. I'm still approaching a carrying capacity. I'm still doing that. But you can see now the overshoot is more. And now there's a lot of oscillations. And now the oscillations seem to persist. And they're growing bigger and bigger there. And so I continue, and I get these oscillations. And I continue, and I get these oscillations. What do you think is going to happen? What's going to happen? Eventually get 0. Any other ideas? Who wants to put money on it? Okay, now something interesting is happening. I seem to be getting 2 kinds of oscillations, big ones and small ones. Okay, keep going. Okay, so now let's start again. We'll have a bigger value for this. Let's try 5. Okay, now I get these oscillations. They come in much more quickly. There I get 2 kinds of oscillations. Now I seem to be getting not quite repeating themselves. Now there seem to be oscillations, but not quite. I get something that looks like it might repeat it. Perhaps it does, but it doesn't repeat it. And as I keep going, you see that the behavior is not very well organized anymore into oscillations. So this kind of behavior is called chaos, because I can't characterize it as a repeatable pattern. If I can characterize it as a repeatable pattern, then I say it's cyclic. But when it's not a repeatable pattern, I say it's chaos. So how does this work? Do you think we can understand how this works graphically? So in days before they had computers, how did they know they were going to get this crazy behavior? Well, you have to have a computer, or you have to do the math to work it out. Well, you can understand this from a graphical technique called cobwebbing. So we're going to go and talk about cobwebbing. I promised I'd build this model. I nearly forgot. Who still wants me to build a model? Okay. Okay, so let's close this. Save before closing? Yeah, okay. Let's close that. Okay, so now we go to Nova, and we'll open it. So we'll start from scratch. There Nova is. Double click on it, and it's coming up. Okay, so I can save it and give it a name. Okay. So I'll just give it the name September 2. You give it a more meaningful name, like Generalized Beaverton Holt. I'll just call it, because I already got one called September 2. Okay. So now I'm sitting there with my open canvas. What do I do? How do I start? I get a stock. I get that thing called X, and I'm going to model. So I've actually got bifocals. I just got these over the weekend, and I thought they were going to be fabulous, and they're just horrible. If I look out the side, nothing's in focus. If I look out there, nothing's in focus. But it's supposed to help me look at you and look there with the same pair of glasses. So if the optician says, do you want bifocals? Say no. Or say you want the ones with the lines down here. But he said, we got these new digital ones, and they're just amazing, and everything's done digitally by computer, and they calculate everything. But it doesn't work very well. So I'm going to see if I can use them. Okay, so I go to components. Here's my stock, and I'm going to just call it X. Okay. I don't think I'm going to use it. It's just terrible. Okay, don't get old. So by the time you get to my age, they'll probably have bionic eyes for you. Okay, and I'm going to open this by right-clicking, and I'm going to set the initial condition to, what should we set it to? I can't remember what we need to set it to. I'll just set it to 100. And then I'm going to set this to sequence. So this name has changed. In earlier versions, it's called discrete. So some of you might see discrete. It depends which version you have. It was just changed recently. Okay, so I've done that, and it turns purple. Now I'm going to get this thing called a flow, and I'm going to call this RHS, right-hand side eqn of the equation. So this is actually just the right-hand side of the equation. I'm going to connect it to my stock. So I use this to build the right-hand side. And when I look at the right-hand side, how many different parameters do I have? 3. I have R and K and G. So I'm going to go over here, and I'm going to put down one that I'll call R, okay, and one that I'll call K, and one that I'll call G. Okay. Now, in order to express the right-hand side, I need R, K, G, and X. So I'm going to go to this arrow over here, and I'm going to draw an arrow from R to the equation, G to the equation, K to the equation, and X to the equation. Okay? You'll get better at doing this. To begin with, it may seem a bit sticky, but you'll get used to that. And then I open this, and I'm now going to formulate this as an equation. So I'm going to say that this is R, and then I have to move the arrow into the right-hand box in order to type something in. And for multiplication, you just use the star. And I'm going to multiply it by X. Now, here, I could just type in X. I don't have to choose this X. I could type in X. But it's going to matter if that's a lowercase x and you type in an uppercase X, it won't work. So that's why it's better sometimes to choose it rather than to type it, because you might, by mistake, mistype its name. And so now we're going to divide, so it's just the backslash. And now I'm going to open parentheses, because I'm going to have to express this term. And this term is going to be 1 plus. Now I'm going to take the ratio of x to k to the power g, to the power gamma or g. When you're working with JavaScript, in some programs, you can use the array like that. And that means x to the power g. Some of you can't see what's going on, okay. But in Java, you've got to write math.pow, the base and the exponent. So you've got to write it like that. Okay, that's the only slightly unusual thing here. That's it. So otherwise, I'm going to type math.pow, open parentheses, close parentheses. And then in here, I'm going to put x divided by k, comma, g. Okay? And I've got a lowercase x and an uppercase k, because that's what I used. Okay? And now this is almost ready, but I want to see the output. So I can either make a table by choosing that. As you can see, it says table there. Or I can take a graph by choosing this. And I'll put this graph down here, and I'll call the graph output, or sequence, or trajectory, whatever you want to call it. And then I'm going to open this table by right-clicking, and I'm going to select the thing that I want to look at. I want to look at x. And OK. And now you'll see that this method must be discrete here, because and delta t is automatically 1, and I want this to run for 50 rather than 12. And this thing over here, I can pull it over so that I can see it. And I think I'm ready to go. And if it doesn't work, then I'm going to have to look why. So capture, load, exec. OK, cannot find error in x. So maybe I typed, oh, I left, okay, good spot, okay. Capture, load, exec, okay, that seemed to work. Now what I need to do is I need to change these values. So let's see what I've got for g here. For g I've got 0, that's not going to help, so I'll take 2, okay. For k I've got 0, that's not going to do anything, so I put 100. And in here, let's see, I've got an initial condition, I'll take the initial condition, let's say 50. And hopefully this will run now. Okay, it still drops very rapidly to 0. G is 2. The R, what did I do with the R? R is 0, okay. So what should I say? R is equal to 1.5, okay. So there are lots of things that can go wrong, and you don't get very good error messages. There, worked. Okay, so now in order to get what I've got, you have to get sliders. So let's take a slider for R. And I'll call this R slider, okay. And I'll allow R to go from 1 to 10 in units of 0.1, okay. And you'll see that the slider appears there, and it appears over here. Now, what I want R, instead of having a value 1.5, I want it to take on the value of the slider. So I go slider, okay. And now I can say, okay, capture, load, exec, and then I can run it for different values of R. Every time I change it, I've got to exec again. And if I change it, I've got to exec again, or I can put it in auto mode. And in auto mode, then when I change it, it'll run. And then if I want to compare things, I put compare, and then every time I run it, it'll keep the last one. So it doesn't get rid of them. So you've got normal and compare. And then I can make the slider for G. And so you've seen how that model works. I'm not going to go into it anymore. Okay. So now I promised you that graphically, we can see what's going on by doing this procedure called cobwebbing. Okay, so let's bring up these lecture notes, and let's go on to cobwebbing. So cobwebbing, another way to visualize sequences, and I can make this a little bigger. You want me to make it bigger? Let's see, 80. Okay. Another way to visualize sequences determined by a difference equation, and in the book we're using A for sequences, not X. We use X in our model, we use A in the sequences, is to plot the function y equals f of x and y equals x. So what I said is we plot here f of x equals x, that's y equals x, and then we plot the function y equals that function, and we do it on an x, y, and then we think of x as the current value and y as the next value. And so we call x x of t and y x of t plus 1. And so you go through this process, and we'll just have a look at how this is done. And I'll have a look here for the square root function. Okay, so let's see what happens when f of x is equal to the square root function. So if you draw the square root function, it goes through the point here, 1, 1. And to begin with, it's larger than y equals x, and then it's smaller than y equals x. Everybody knows what the square root function looks like? Okay, so if I were to draw a quadratic function, this is x, this is y.